So the next thing we're going to do is talk about density of gas and do one more thing about something called gas stoichiometry. So let's start with the density of a gas. As you can see, I know there's a lot of equations. You had Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, all put together into a combined gas law. Then we also came up with the ideal gas law, PV equals nRT. That was the last lecture. Today, this is not necessarily a specific separate gas law. It's actually, this is derived, the density of a gas. Density is equal to mass over volume. We actually derived this equation that the density is equal to pressure times molar mass of gas divided by R and T. And that actually comes from the ideal gas law, PV equals nRT. Because if I substituted V, PV equals nRT, V is equal to nRT over P, and I substitute it in, and it just happens to be the number of moles, N divided by volume is the molar mass. So that's kind of where this came from. But I don't really want to go there right now. This is actually not actually, it's kind of like if density is mass over volume, you can rearrange that D equals M over V. You can rearrange this equation to D times V over equals to M. While rearranging density equation using ideal gas law, we actually get this. The density of a gas is equal to the pressure of the gas times, this is like italicized M, capital M, molar mass of a gas. Molar mass, which is grams per mole. How do you find molar mass? If you're not given it, let's say you're given it's carbon dioxide. How do I find a molar mass of carbon dioxide? You need to get a periodic table, look up carbon and 2 oxygens, because that's what carbon dioxide is, add that up for the molar mass. So that's what the molar mass is in grams per mole. Divide by R and T. R, the same gas constant, T, temperature. In this chapter, all temperature are in kelvins. There will be never 0 degrees Celsius. That's 273 kelvins. There are no, it's only in kelvins in this chapter. Rearranging D is equal to PM over RT. M is equal to DRT over P. These two are the same equation. Just rearrange. Solve for M. Multiply both sides by RT, DRT. Divide by P, and that's what M is. So molar mass of a gas is equal to dRT over P. The density times R, the gas constant, times temperature over pressure, where the density of a gas is measured in grams per liter. So D, the density will be in grams per liter. Okay, probably just easier if you just see a sample question. And that's what the next slide is, if I can get to it. There we go. Okay, a 2.10 liter vessel or container. It holds or contains 4.65 grams of a gas at 1 atmosphere and 27 degrees Celsius. What's the molar mass of the gas? Okay, well, I'm trying to solve for the italicized capital M. That's, going back, this equation. I could use this if I just solve for M, I get this. They are the same equation. So molar mass of gas is equal to dRT over P. The molar mass of the gas is equal to dRT over P. I need to know the density. I need to know R. Actually, you always know R. It's the gas constant, 0.0821 liters atmospheres over mole Kelvin, times temperature over pressure. So I need to know dRT over P. There's a few that we already know. Obviously, you know R already. R is the gas constant. I know the temperature, 27 degrees Celsius. It's just you need to convert to Kelvin. So I know the pressure. Or do I? Yeah, it says so. It's 1 atmosphere. So I know R, I know T, I know P. I just need to kind of solve for D. I really just need to solve for D. D, density, is mass over volume. Do I know the mass, which is grams? Do I know the volume, which is liters? Yeah, it says so. It's 4.65 grams of gas in a 2.10 liters. You know the mass, you know the volume, divide. I get 2.21 grams per liter. I know D, I know R, I know the temperature, I know the pressure. Plug it into the equation. D, this is R, this is always R, 0.0821 liters atmospheres per mole Kelvin is a constant. And these are the units of R always. Times the temperature. I converted 27 degrees Celsius into Kelvin by adding 273.15, divided by the pressure, 1 atmosphere. Okay, It's just written as 1, but technically 1.0036 sig figs. Now, let's not worry about sig figs right now. But, so the answer would be 2.21 times 0.0821 times 300.15. So what is the answer for this thing? Well, liters and liters cancel. Kelvins, Kelvin cancel. Atmospheres and atmosphere cancel. Molar mass is grams per mole. Divide in or multiply that all in a calculator. And I get 54.6 grams per mole. So 54.6 grams per mole is the molar mass of this gas. So before you're like, what's the molar mass? You might have thought like, well, look it up on a periodic table. Notice you weren't given what this gas is. It's like some unknown gas. So you don't know the formula. But even though I don't know the formula of this gas, whether it's carbon dioxide or what, it's unknown, I can calculate the molar mass of this gas. Okay, so that's one of the beauties of this equation. Okay, next thing that you'll like, not really, gas stoichiometry. Okay, so gas stoichiometry is actually not that hard. It's really just gas laws and stoichiometry. So this chapter is all about gas laws, but stoichiometry all added in. One way to do it is change your amount of gas in grams or volume into moles, moles to moles using your balance equation, and moles into whatever it is that you're trying to find. It's just easier. Always look at a sample question. Let me move my face. I'll move it over on top of that thing. Okay, so the question says, what is the volume of carbon dioxide, so I know what gas this is, produced at 37 degrees Celsius, so I know the temperature, and 1 atmosphere, I know the pressure, when 5.6 grams of glucose, that's glucose by the way, are used up in the reaction. C6H12O6 is glucose. Anyone who has had biology already should know that. Even if you didn't know that's glucose, obviously that's oxygen, that's carbon dioxide, and that's water. Process of elimination, not the water one, not carbon dioxide, not oxygen. The weird look to you, if you didn't know this is glucose, the weirder looking one, that's probably glucose. Okay, but that's also how in this, if you're given this problem, I would have told you that's glucose, but in case you didn't know, yes, C6H12O6 is glucose, simple sugar, something your body metabolizes or uses up. Okay, so I'm trying to find the volume of carbon dioxide is the question. So somehow, and I know I have to use a gas law, I have to know PV equals nRT, so I have to somehow solve for volume. If PV equals nRT, then, okay, if PV equals, I'm getting ahead of myself. If PV equals nRT, I'm trying to solve for the volume, is what I'm trying to end up at. I need to know if PV equals nRT, V is equal to nRT over V. Well, I know the temperature, I know the pressure. What I need to figure out is the number of moles of, and you always know R, I need to figure out the moles of carbon dioxide. And how do I find the moles of carbon dioxide? Given grams of glucose, stoichiometry. If I was given 5.6 grams of glucose in this balanced equation, it's already balanced. All I know is 1 mole of glucose makes 6 moles of carbon dioxide. 1 mole, coefficient 1 mole of glucose makes 6 moles of carbon dioxide. But I'm given grams, not moles. First step, change grams to moles. Change grams to moles by dividing by molar mass. How do I find this molar mass is 180.18? I only had 3 sig figs there. How do I know the molar mass is 180.18? Add up 6 times carbon on a periodic table, 12 times hydrogen on a periodic table, 6 times oxygen on a periodic table. Carbon is 12.01, hydrogen 1.01, oxygen periodic table 16. Add that all up is 80.18. Okay, so I changed grams to moles. Now I just need to change moles of carbon dioxide into moles. So moles of, this is glucose, moles of glucose into moles of carbon dioxide. I know that from the ratio 6:1. 6 moles of carbon dioxide is formed for every 1 mole of glucose. Coefficient 6, 6 moles of carbon dioxide is formed for every 1 mole of glucose. From that, I can now figure out how many moles of carbon dioxide. Notice grams of this is glucose. Grams of glucose cancels, moles of glucose cancels. The moles of carbon dioxide that you have left, 5.6 times 6 divided by 180 type that on a calculator. What is 5.6 times 6 divided by 180? If you did that, you should have 0.187 moles of carbon dioxide. So great, now you found the number of moles of carbon dioxide. That's not the question. But you need that moles of carbon dioxide to calculate the volume of carbon dioxide. How? PV equals nRT, or V is equal to nRT over P. This is N. You know R is a gas constant. You know the temperature, just convert to kelvins. You know the pressure, it's 1. Plug it in. You know N, we calculated it, it's at 0.187. You always know R, 0.0821 liters atmospheres per mole Kelvin. Kind of like you always know pi is 3.14. I know there's more digits, but 3.14 is pi. R is 0.0821 liters atmospheres per mole Kelvin. We know the temperature, 37 degrees, is 310.15 kelvins. I know the pressure, 1 atmosphere. So what is the final answer? It'll be 0.187 times 0.0821 times 310.15 divided by 1. Okay, if you did that in a calculator, you should see, oh wait, first of all, units, moles and moles cancel, kelvins and atmospheres and atmospheres cancel, kelvins and kelvins cancel. The only unit left are liters. On your calculator, you should have gotten 4.76 liters. So that is the volume of the gas. So that's the volume of the gas of carbon dioxide produced at 37 degrees Celsius and 1 atmosphere if 5.6 grams of glucose are used up in a reaction. And this is actually kind of a reaction that would happen inside you. Human body is about 37 degrees Celsius. We're at sea level. If you consumed 5.6 grams of simple sugar, this is simple sugar. If you ate 5.6 grams of simple sugar, how much carbon dioxide could be produced in the reaction? And that's the gas you would be exhaling. So if you ate 5.6 grams of glucose for your body to metabolize it or to use it up from oxygen that you're breathing, you would give off 4.76 liters of carbon dioxide out of your breath, or as you're breathing. So that's kind of an example, like a real example of where this gas laws and gas stoichiometry is used. Just check if we have the next slide. Okay, no, we don't need that yet. Okay, so that is gas stoichiometry, and example of where we use density of a gas.